Okay, so it's going to be a short video. Well, you can tell by looking at I guess down here to see um, how this video worked out. Here's the question. It's 3.21, page 34. Is the given vector in the set generated by the given set? So, comment about vectors. Let's go back to 2D. It's easy to see. Suppose we have this vector here, and it's the vector u. And here we have the vector v. We have two vectors. There are many ways to come about the way to add two vectors. There's many ways to motivate how we do it. It's simple. We add the x coordinates and we add the y coordinates. So the way you do it is simple. Just a really quick, simple example. Let's suppose you had the vectors, and I'll write them like this. I could write them traditionally like ordered pairs. It means the same thing. But suppose we had 4, 1, and there's a vector, and we have the vector -1, 3. How do we add these two? We just come up with the vector 4 plus -1, comma, 1 plus 3. So 3, 4. Now that's an algebraic approach. It's simple and it's intuitively obvious. I think that's what everybody would do. How do you multiply a vector by a real number? And I just said I'd write it this way, but I wrote it, I could have just as well written it like this. Look, 4, 1 plus -1, 3, which is primarily how our book is doing, and me too in this course. Now, how should we, for example, go about multiplying a vector by a scalar, by a constant? So let's say we have this vector. There's a vector 3, 5, and we want to multiply it by the number 2. Well, we just take 3 times 2 and 5 times 2. So it's the vector 6, 10. Again, that seems like a pretty obvious thing to do, and even if it's not, it seems pretty easy. But is there another way to look at it, to view it? And the answer is yes, absolutely, geometrically. Both these situations, both addition and multiplication. So as far as addition goes, and even this, there's several ways to look at it, but probably the way you'll see most is this. If you want to consider the vector u plus v, what that means is go out along u till you're at the head of u. Remember, vectors can be simultaneously thought about as these arrows and actually that point at the end. So I could just as well have said, consider this point or go to that point. Once you're at that point, place this vector there. Now, the book points this out, and it's absolutely true. Vectors, this is a vector right here. A vector is an arrow. It doesn't necessarily go anywhere. It just has a length and a direction. You can put it anywhere you want to. So actually, the way we define that, if you want to get real, I'm thinking right now, if you wanted to write it really technically correct, a vector is actually a set of arrows. And what they all have in common, the properties they all possess, are the same length and the same direction. However, sort of the standard way to think of these vectors is where the tail of the arrow is right at the origin. And that's really the conventional way of thinking of it, but you can move them around. So what we do is we take this vector v and we place it out over here, and that really is still vector v. And now go from the origin out to here, and that is u plus v. Now that gives us a visual meaning for the vector v. Now subtraction is interesting. Let me just write a fresh picture here, and let's look at subtraction. Here's the vector u. Here's the vector v. And we did u plus v. Well, how about u minus v? U minus v. Let's call it w. Well, what does it mean? Well, we could go back to the algebraic approach, and we would just subtract the x coordinates and subtract the y coordinates. That's what you do. Simple, straightforward, obvious. Okay. But what does it mean geometrically? Well, let's just think about real numbers. Just think about real numbers for a second. A minus b equals c. What do you even mean by that? I mean, if you were explaining this to someone who had never learned arithmetic, you're not born knowing this, so you would have to explain to them. Now, I guess the most obvious thing is you would say you would take whole numbers, like 9 minus 3, and you would take 9 apples and take away 3 apples. That's true. That's what you would do. In fact, let's consider this for a second. 9 minus 3 equals 6. But there's another way to look at it, and you could say that this is the number that you have to add to this to get that. 6 plus 3 is 9. That really is another way to look at it, which is to say this is equivalent. So when I say equivalent, I mean exactly the same thing. There's no difference in the way you say this. And oftentimes you're going to see this symbol right here, IFF. And it stands for if and only if. And that's the formal logical way of saying this. You're saying this is true if this is this, and it's only true if that is that. But we don't need to worry too much about the logic here, except to say they're the same thing. So what does this mean? It's equivalent to saying that A is equal to C plus B. So this is the thing you got to add to this to get this. This is the thing you got to add to this to get this. Let's do that with vectors. W is the thing you have to add to V to get U. W is the vector you have to add to V to get U. So let's see, what would I have to add to V to get out to U? I would have to add this arrow. So this arrow, this vector right here, this is U minus V. And you could try to remember this in a variety of different ways. Most people, I think, just remember if you have U minus V, you construct the arrow from V to U in this direction. For some reason, I don't ever trust my memory, so I just always kind of flash back to this. And I think, okay, V's the thing that we add to V to get U. And if you're at V, what do you got to add to it to get to U? Well, this. And so there you go. So that's the meaning of the geometrical meaning of subtraction. What about multiplication? What about multiplication? If you have, let's say, U, the vector U, and you want to multiply it by 3, it simply means you're going to take this and stretch its length threefold. Or if you had 1/3, you would contract it to 1/3 of its original length. And if it was negative, you would have it shooting off in the other direction. Okay, so that's all pretty straightforward. Now I want you to consider the following thing. You have two vectors, U and let's say V. And I would like you to consider all the vectors you can construct via a linear combination of these two vectors. What do I mean linear combination? Here's what I mean. You are allowed to multiply either of these two vectors by any real number and then add them together. So what does a linear combination of these two look like? It looks like this, AU plus BV. Now this itself is a vector. And we say that this vector is a linear combination of these two vectors. And there's a lot of other things. There's a lot of other terminology ways of phrasing this. The set, I have to sneeze here. Off camera. The set of all vectors that can be constructed by a linear combination of two given vectors is called the span, S-P-A-N, the span of these two vectors. Now, how would I write that down? Well, I could write it down a whole bunch of different ways, but the span of the vectors U and V is equal to, like I said, it's the set of all vectors that can be constructed with a linear combination of those two vectors. So let's see, what on earth would that look like? Well, I guess we could say it's the set of what? All linear combinations. So how about if we just do this plus BV, where or such that A and B are elements of the real numbers. So that's the span of a set of vectors. These are the vectors. Together they form a set. A set of what? A set of vectors. This is the set of all vectors you get by constructing linear combinations of these two vectors. We call that the span. Just like if two things span something. Now, what is the span of these two vectors? I think geometrically, just to look at it, just use your eyes, is obviously all of the plane. What is this question in the book asking you? It's actually asking you, is this vector in the span of these two vectors? So this is just a different way of asking this, or this is a different way of asking this. It's the same thing. So let me actually see if we can draw a picture here and see if we can answer the question geometrically, and then we'll answer it algebraically. Now, granted, the book just is yes or no question. Yes or no, I guess you'd say yes or no. But it would be nice to give a rationale for your answer, yes or no, because let's face it, got a 50-50 chance of being right if you just guess. These are the two given vectors in the problem. So again, we're on problem 3.21, page 34. Look at these two. This is the vector 1, 4. So we go out 1 and up 4. 1, 2, 3, 4. So right there, there's the first vector. This vector right here is the vector 1, 5. So out 1 and up 5. So like that. And the question is, can you get this vector as a linear combination of these two vectors? So 2, 3, 1, 2, 3 is up here like this. By applying the right scalars to these two vectors, I should label this here, but I don't really know. How about this? Okay, U and V, and this is the vector in question. Can you apply the right scalars? Now, the way I've drawn that, maybe, I don't know whether it's obvious or not. I mean, the answer I can tell you right now, the answer is yes, but is it entirely obvious? I should have drawn a better picture, although it's not that bad of a picture. How can I get this vector by doing these two vectors? Well, let's see. Maybe you could imagine that if you went out far enough this way with vector v, and then by multiplying u by a negative number, you can make it come back like this. So maybe that's possible. This is where algebra is kind of a nice thing. It's easier sometimes in geometry. What are we looking for? We're looking for some real number a, so that we can multiply it by this 1, 4, plus some other real number. We multiply it by the vector 1, 5. Sorry, I keep writing 1/5, I think, because it looks like a fraction, right? But 1/5, and that's supposed to equal to the vector 2, 3. Well, let's go ahead and multiply this out via our definition of how to do scalar multiplication of vectors and addition of vectors. What does this look like right here? It looks like a 4a plus b 5b, and that's supposed to equal the vector 2, 3. Well, let's add this up. That's the vector a plus b and 4a plus 5b, and that's supposed to equal the vector 2, 3. Well, what do we have? We have a system of two equations and two unknowns. So of course, that's what this question boils down to. So what is it? What are we looking for? A plus b equals 2, and 4a plus 5b equals 3. Hey, just to change things up a little bit, just for fun of it, let's solve this with substitution. We've done enough elimination for today. So right here, we'll get a equals 2 minus b. Let's put that in for, a right there. So 4 times that would be 8 minus 4b plus 5b equals 3. So b equals, we'll subtract that from both sides and get what? Negative 5. So b equals negative 5. Put a negative 5 in there. A equals 7. So now the question didn't ask us if it was yes or no. The answer is yes. Why is it yes? Because we were able to solve this system and we gave the solution. If you want to, you could throw it back in there, but there's no reason to do that. What would be kind of nice, I suppose, is if we had some software that would graphically show this. So what would we want to see on the software? We want to be able to somehow enter this vector 1, 4, and then multiply it by a, which is 7, and add it to this vector, or this, negative 5 times this vector. Maybe I need an out here. And that's supposed to equal this vector 2, 3. So it would be nice if it would draw these two vectors and then scale those two vectors and then add them together to look like a nice parallelogram, where the diagonal across the parallelogram would look like this. And if we did everything right, that's exactly what it should look like. Okay, so there's that question. I'll probably have 1 or 2 more videos coming up. It might not be till later tonight, but I'll get them done. It'll just be either discussing more topics within chapter 1. So you'll see as you look ahead, I can't remember the section. In fact, let me find this section right now. All this business about adding vectors and multiplying them, That comes from, and it's just, well, it's page 35 is where it starts. It's called linear geometry. And I already discussed that a fair amount, I think, in class. I mean, again, chapter 1 is all part and parcel of one major topic. Um, um, we're going to finish all of chapter 1 here. But what I'll do is I'll come back with a video, and I'll probably work a couple more problems from the book and maybe discuss a little more theory. So remember, in the meantime, definitely keep working on your homework problems, okay? And keep an eye out for more videos to replace the abandoned Google Meet this morning.